Oops. Okay. Sorry, Zoom's a little bit finicky the way it moves things around when I click on a button. There we go. Okay. So let me maybe start with just some announcements just to kind of remind you some things that we talked about on Monday. Monday's lesson is online, so I was a little bit late about posting things, but I did get it posted late last night. So hopefully you'll be able to see everything right there on YouTube. Sorry, there's too many windows open here. Also, I'll have office hours at the usual time, so they'll be after class today at 11, and then also in the afternoon at 4 o'clock. Mentor sessions are still being held, so Sundays, Mondays, Tuesdays, and Thursdays from 6 to 8. And just as a reminder, we only have 2 more assignments to go. So problem set number 12 will be due this coming Friday, and problem set number 6 will be due next week on Wednesday. And then after that, that's it. Nothing else is due. I know that some of you haven't had a chance to turn in things. I'm being really laid back, really flexible. Whatever you want to turn in, if you need like 2 to 3 more weeks to turn in stuff, I'm perfectly happy with that. Certainly take your time, do the best you can. Even if you feel that you're not going to be able to get everything turned in, I would say don't stress out over it. Just send me an email, let me know. So that way I can kind of keep track with the graders to let them know what's happening. All right. This whole thing of midterm versus final presentation. So just wanted to remind you where things stand on that. You have the option of either taking midterm number 2 or giving a final presentation. For midterm number 2, the plan is to post it on Sakai on Wednesday, April 24th, and then you can take as much time as you need as long as you turn it in Monday, April 27th by 5 p.m. So that's the plan right now with midterm number 2. I plan on doing a review for the midterm next week. So the plan right now is that we'll have the problems that we'll do in class for problem set number 6 on Wednesday, and then I'll do the review for the second midterm that Friday, April 24th. Then after that, you'll have the whole weekend to kind of work on it, do whatever you like, and then we'll meet back on Monday. So then the final presentations, on the other hand, will take place for the next week and a half after that. So if you are going to do a final presentation, all that I ask you to do is the following 3 things. Number 1, pick a group of 2 to 4 people. Number 2, pick a topic, and this will be one of the topics that you see that I have listed here. This is also in the syllabus. If there is a topic here that you don't know more about, I'm happy to chat about it in office hours. If there's a topic not listed here that you want to do, I'm perfectly happy with that as well. Just let me know so that way we don't overlap, but there's another group that wanted to do either the same topic or a similar topic. And these presentations, of course, are all going to be videos. You can either record a video, you could do a live demo during the class period. It should be 20 minutes though, allowing for about 5 minutes of questions and answers. And these will be shown at some point between Monday, April 27th and Friday, May 8th. Right? So that'll be the plan there for the final presentations. Of course, you could do both. So if you wanted to do the midterm number 2 and the final presentation, that is perfectly fine. I will give you extra credit for it. I'm still debating as to the exact percentages, say things like how much the midterm will be worth and what have you. So I'm going to move things around a little bit based on what's in the syllabus. And I'm hoping to get that back to you on Friday. But at least I just wanted to remind you that this is the plan right now, that you can do one or the other. You can either do the midterm number 2 or you can do the final presentation. But you definitely do not have to do both. Okay, any questions on this? Right. Okay, let me do this. I want to take a poll, and I just want to kind of get a show of hands. This is going to be an anonymous poll. So this is non-binding. Don't think that you have to, whatever you answer here is what you're going to do. I just wanted to know your thoughts, whether you wanted to do the second midterm only, the final presentation only, or both the midterm and the final presentation. So I'm hoping that a window has come up for you. Again, it's an anonymous poll. I'm just trying to get a rough idea of what everyone's thinking. I know at least 2 people have told me that they want to do a final presentation. So the point is, if nobody wants to do a final presentation, then we probably won't worry about it. But if a good number of people want to do it, then we'll have to kind of move some things around. So yeah, so again, I just wanted to get an idea. I think everybody has answered. No, actually, I think, yeah, here we go. Now everyone has answered. All right, thank you. So let me show you the results. Right. So this looks good. It looks like the majority of the class does want to do the midterm number 2 by itself. That's kind of what I expected. And then there's a handful of people, roughly a third of the class, that wants to do both the midterm and the final presentation. So, again, this is non-binding. If your mind changes in the next week or so, that's perfectly fine. I just wanted to get a rough idea. So thanks for filling out the poll here. Right. Does anyone have any comments for me about all of this for right now? Okay. All right. Well, thank you very much for that. So let me come back over here, share the screen again. All right. Okay, let's maybe go over some math here. Let me try to recap what it was we focused on Monday. Sorry, this is the typo. It shouldn't be Wednesday, April 8th. So remember that we talked about Cauchy sequences, and we said that for a Cauchy sequence, they are really the same as convergent sequences. So the idea is as follows. The following are equivalent. So a convergent sequence is equivalent to a Cauchy sequence. The difference is, for a convergent sequence, you have to already know at the start what the limit L is. So the definition of convergence just means, given epsilon positive, we can find a delta such that xn minus L is less than delta in absolute value whenever n is greater than delta. Right, but notice that this has an emphasis on L. You need to know what L is before you can do anything else. On the other hand, for a Cauchy sequence, the definition is, given a positive epsilon, there exists a delta such that xm minus xn in absolute value is less than epsilon whenever m and n are greater than delta. Right. So now with the Cauchy sequences, you don't need to know what the limit is, but the nice thing is that once you know that the terms in a sequence are close together, then you know that a limit does exist. Right, so this is kind of the pros and cons, whether you want to do Cauchy or convergent. Convergent might be easier if you already know what the limit is. Cauchy might be easier if you don't know what the limit is, but you know something about how the terms are getting closer and closer together. Okay. Once we have a Cauchy sequence, we realize that there's some arithmetic we can do. So we said that if x and y are Cauchy sequences, then the sum is a Cauchy sequence, and also the product is a Cauchy sequence. So I'm going to come back towards the end of the lecture today, and I'm going to try to hit home these 2 ideas, but in a totally different way. Right, so again, if you have 2 Cauchy sequences, x and y, the sum of 2 Cauchy sequences is a Cauchy sequence, and the product of 2 Cauchy sequences is a Cauchy sequence. Right, so any questions up to this point? Okay. All right. Now, last time we talked about this idea of continuous functions. So I want to remind you some of the definitions we were going over here. First of all, I need to talk about what a closed interval is. So the closed interval from A to B is just the set of numbers between A and B, but X might equal A or X might equal B. So that's just what we mean by a closed interval. It's just the numbers from A to B, but we're going to include A and include B. Right. In the homework assignments, you've been seeing things like open intervals, but for this class, we really want to focus on these closed intervals. A function, of course, which we'll write f, a function defined on a closed interval I, just means that given any x in the interval I, then f of x is well-defined and unique. Right? The uniqueness just means that it's the vertical line test. Right? So given x, then I know exactly what f of x is. Right? So that's what we mean by a function. Given a point P in our closed interval, we'll say that our function is continuous at P if two things happen. One, f of P exists, so that is, it's defined and unique, so I know what f of P is, I can compute it. And number two, given a positive epsilon, there exists a delta such that f of x minus L is less than epsilon whenever x minus P is less than delta. Right? That's what we mean to be continuous. There's really two things. First, f of P has to exist. And second, we have this weird epsilon delta definition. So what I want to do today is try to go over a couple of examples, give some applications, maybe also discuss what are a couple of other ways in which you can think about this really weird definition here. But this is what it means to be continuous at a specific point P. Of course, if one of these two does not hold, we'll say that f is discontinuous at P. So I need 1 and 2 to both hold. If either one of those does not hold, we'll say that it's discontinuous. And then finally, if it's continuous at every point P, then we'll say that it's continuous on the closed interval I. Okay, any questions on this? Okay. Here's a result that we stated at the end of the last lesson, and I do want to go over this again today. Say that we have a continuous function f on a closed interval from A to B. Then if you give me any convergent sequence where let's say P here is the limit, then f of P is the limit over here. Right, so again, if xn's go to P, then the f of xn's tend to f of P. Right, so the nice thing about a continuous function is that I can kind of apply f to both sides if I have a sequence here. Right, that's kind of the intuition. Now remember that there is a different way in which you can kind of think of sequences, and this is the idea of supremum and infimum. So here's another way to do sequences using infimums and supremums. Again, say that we have a continuous function, and let's pick a subset S from I. Right, so this subset could be things like, it could be a sequence, it could be a Dedekind cut. Well, technically it can't be a Dedekind cut in this case here, but it could be like any set that you want. Absolutely any subset of I. Well, because I is this closed interval, both the supremum and the infimum lie in this set. So you kind of had a homework assignment that looked like this, but this is just reminding you what you did in this problem set. So again, if you have a subset of a closed interval, then both the supremum and the infimum are numbers in this set. Next, if we have a function that's increasing, right, so increasing just means this here. You can almost think of like increasing sequences. So whenever x is less than y, f of x is less than f of y. That's just what it means to be increasing. So then what this says is, roughly speaking, you can pull the supremum to the outside. So remember that the supremum of S is some number, whereas f of S is some set. So if I want the supremum of that set, then I just have to take f evaluated at the supremum of the set. Right, so we're going to talk about this a little bit more today. And it's a similar statement if it's decreasing. So of course, decreasing just means that f of x is greater than f of y whenever x is less than y. And it's the same idea, that the supremum is some number. So if I take f evaluated at that number, that's the same thing as the infimum of f of the set. Right, so I do want to go over an example that kind of explains a little bit what these two statements mean here. Okay. All right, so any questions on these statements? All right. Okay, let's maybe try to go over some examples here to get an idea of what all of this means. So this is the same example that we covered on Monday. So let's take a look at our quadratic polynomial. F of x is x squared. So we know that this is continuous. If you don't believe me, we're actually going to prove this today. But let's just say that we know that this here is continuous for all real numbers. Now let me write down the following two sequences. I should say the following sequence. So first, this is defined recursively, where x0 is equal to 1 and xn plus 1 we can write in this way here. Now we proved in a previous class that the limit of this sequence is the square root of d. Right, so we know that if we have this sequence here, then the limit is the square root of d. So we proved this earlier. Now, according to the two previous propositions, because f is continuous, f of xn, all I have to do is just plug in square root of d for x. But of course, the square of the square root of d is just d. Right. So again, the first statement here we proved in class. And the second statement here is just that previous proposition that I just showed you. Right. Now, what we could do is we could just look at all of this numerically. So over here, for the xn's, we have an increasing sequence. Right? This is monotone increasing. So according to that proposition, our function f of x, of course, this is an increasing function. I mean, you can just plot it. You can see that it's an increasing function. So then that means that the sequence over here, f of xn, also has to be increasing. So what that previous proposition said was, whatever the supremum of the set of xn's is, that has to be the supremum of the set of f of xn's. So I take the supremum over here, which of course is radical 2, and if I evaluate that for f, that'll be the supremum for this set over here. Right, so notice that that's exactly the same as making these two statements. Right, so I'll say that one more time. Here you have an increasing sequence, so I can look at its supremum. The supremum will be this number, so that's the square root of 5 in this case. If I evaluate that number into f, again, evaluate the supremum into f, then I find the supremum of this set. The supremum of this set is the square root of 5 squared, which is just 5. Right, so that's just what that previous slide said. Okay. All right, any questions on this example here? Okay, all right, let's try another example. Again, this is the same example that we did on Monday. Now let's take a look at this sequence. So again, we proved in an earlier class that the limit here is the square root of d. And so according to the proposition, if I evaluate that into f, then I should get back d, right? Just square at the square root of d. And so we can see all of this using numbers again. So this sequence I chose because remember that this is a monotone decreasing sequence. So the numbers here start at D and then they decrease down to the square root of D. So in this case, same idea. I can ask about, let's say now, the infimum. Right, so this here will be the infimum, the square root of 2. I plug that back into F, and then that should be the infimum of this set, right? Which in this case here is just the square root of 2 squared, which is 2. Right, so here, we can try this over here with this example. So here I have a sequence. I can look at the infimum, which is the square root of 5. I plug that here into this F, and that should be the infimum of this here, right? The square root of 5 squared is just 5. Right? So that's what that previous proposition said. If I have an increasing function, I can take a look at the infimum of this sequence over here, plug that back in over here, and then that should be the infimum of this sequence over here. All right, so any questions here on what we said last time about sequences for continuous functions? Okay, so today, what I'd like to do is introduce 3 theorems that hold for any continuous function. So I really want to break this up over 2 lessons. Today I want to introduce a lot of these theorems, talk about some of the proofs, and then on Friday I want to review a lot of this and then try to go over some examples. So this is going to be in 2 parts. So the first theorem is what's called the Intermediate Value Theorem. So again, let's let f here be a continuous function. So this says, let L be any number between f of a and f of b. All right, so any number that's in between these 2 numbers. Then the statement is that there exists a point in the interval that equals to that value. All right, so if L is anything between f of a and f of b, there exists a p such that f of p equals L. So what you could say is f attains all of its intermediate values, or all of the values in between f of a and f of b. That's what we call this the intermediate value theorem. So if you have any value, intermediate value between f of a and f of b, call that L. So you can find a point P where f of p equals L. All right, so that's the first of the 3 propositions that I want to discuss today. Okay, so any questions about the statement of this one? Of course, we'll try to prove it later. All right, let's move on. The second theorem is called the Boundedness Theorem. So again, say that we have a continuous function. So then this says that there exists a lowercase m and an uppercase m such that f of x is bounded in between. In other words, every continuous function on a closed interval is bounded. This is all that we're saying. As long as we have a closed interval I, our function is bounded. Okay, so that's the second theorem. That's our so-called boundedness theorem. So you'll probably notice that this looks very similar to what we said about things like Cauchy sequences and convergent sequences. So if a sequence is Cauchy, it has to be bounded. If a sequence is convergent, it has to be bounded. It's going to be the same concept here. Right? In fact, the proof is almost going to be the same as well. And then the third one is what's called the Extreme Value Theorem. So again, say that we have a continuous function, and this says, first of all, there exists a C where f of x is less than or equal to f of c for all x. So not only does f have a maximum, but the function attains its maximum. So there is a C where f of c is the maximum, But the point is that there is a C in the interval where this is the case. So yes, not only does F have a maximum, that's what we kind of proved in the previous proposition with the boundedness theorem, but this stays even stronger. There is a place C where it hits it right on the nose. Similarly, there exists a D where f of D is less than or equal to f of x. So my f of D here is the minimum for the function. And the important thing is here that there is a place where my f hits the minimum right on the nose. Right, so again, we know that a minimum exists, again, by the boundedness theorem, but the difference is in the extreme value theorem, it says there is a place where it hits that minimum right on the nose. Right, so again, this is what the extreme value theorem says. Okay. All right, so any questions on this one, the extreme value theorem? All right. So let's maybe try to give an example to explain what do all three of these theorems say. So I want to discuss this example here. And of course, this here is just the graph of some cubic polynomial. And what we can do now is, instead of looking at the whole graph, let's just block off an interval. Okay. So maybe let's say perhaps this point here is what we're calling A. And then let's say perhaps this point over here is maybe what we're calling B. Right? So then my interval is just going to be this thing here. Right? So everything between A and B. All right. So what the intermediate value theorem says is this. We have here f of A, right? That'll be this height here. Sorry, it's not the easiest thing to draw on here. Let's try this. Right, so that's my f of A. That's going to be some height. And then similarly here, I have some f of B. Right, because I have my B over here, so my f of B is down here. So here's my f of A and f of B. Well, let's pick a point here. Let's call that L. Right, so again, f of A is the height, f of B here is the height. So I'm going to pick some L in between f of A and f of B. So that says, if I kind of follow this all the way down, that has to hit at some point P here. Right, so again, my L here hits here at this P, and this has to be this P. Right? So this is why the intermediate value theorem holds for this function. So again, I have my A that corresponds to this f of A, I have my B that corresponds to this f of B. I look now at the region here between A and B, call this maybe some point L, that will hit here at some point P. Right, so that's the first part of the proposition. That's what we're calling the intermediate value theorem. Okay, so any questions here on this example? Okay. All right, let's keep going. What about the boundedness theorem? So the boundedness theorem says, again, if we have our interval from A to B, then my function has an upper bound. In this case, I can maybe let the upper bound be this here. This will be my capital M. And then I'll have some lower bound. Maybe I'll call this here my lowercase m. Right, because the function never goes below this lowercase m here. and the function never goes above this uppercase here. Right? So that's what the boundedness theorem says, that no matter what, I'm always going to be bounded in between these two regions, lowercase m and uppercase m. Okay, does that kind of make sense for the boundedness theorem? All right. Now, the third statement is the extreme value theorem. So you'll notice that even though m here is an upper bound, it's not a very good upper bound. Right? I could kind of get a little bit closer and I could say, well, this here looks like a good upper bound. So whatever this upper bound is here, this should correspond to maybe f of c. And that c, of course, has to be maybe this point here. Right. So in my interval from a to b, my f of c is the largest value. So that is this here. So again, my f of c is larger than everything else here in the graph. Right. So again, I can find a point c where I hit this right on the nose. Similarly, I can come down here and I see this f of d, which here is the lowest point, and that, of course, has to hit here at some point, which we'll call here d. So again, the d here is the lowest point, and that I know that I'm hitting here on the curve right on the nose. Right, so that's what the extreme value theorem says, that there should be some point c that corresponds exactly to the highest point, and then there should be some point d that corresponds exactly to the lowest point. Okay, any questions about this example then, about these three propositions? Okay, well, let's try to actually go over the proofs of these three here. All right, so let's start with the intermediate value theorem. So of course, what we're trying to prove is between f of a and f of b, we're going to be given some number L, and we want to find a point P that hits L right on the nose. So for the moment, without loss of generality, let's say that f of a is less than f of b. If this isn't the case, you can kind of reverse the symbols, but just for the moment, let's say that f of a is less than f of b. What I'm going to do is consider the following set S. So this is the set of x such that f of x is not greater than L. So if I have like a graph, I'm looking at the set of x where everything is below L. Right, that's kind of the idea. Well, the set is non-empty because A is in S, and the set is bounded because S is contained in our closed region, closed interval I. So this means that there is some P, which I'm going to call the supremum of S, that has to exist. So what we're actually going to show is that f of P is L. Right, so remember that L is going to be some number between f of A and f of B. So now we're going to form the set S, which is kind of everything that looks like it's below L. This here has a least upper bound. So I'm going to prove that if I evaluate that least upper bound, I should get back L. And the reality is the way that we're going to prove that is that we have this inequality here for every epsilon. Okay. All right. Well, our f is continuous. So what that means is, given epsilon, we know that f of x minus f of p in absolute value is less than epsilon whenever x minus p is less than delta. That's just what it means to be continuous at p. And p is in our interval. We know that our function is continuous at every point in the interval. So what I'm going to do is I'm going to unwrap what this here means. So if I say f of x minus p less than epsilon, that actually means this. Right. So again, when I write f of x minus f of p less than epsilon in absolute value, that really means this double inequality here. Similarly, when I write x minus p is less than delta, that means this double inequality here. Okay. All right, so we okay so far? Right, so again, just using the fact that my f is continuous and just writing this out in terms of epsilon and delta. Now, here's the idea. If I go back to this, then I want to stare at the fact that p was the supremum. So that means, remember, supremum means upper bound. So I'm going to break this here into two parts. I'm going to look at everything less than p and then everything greater than p. So for the moment, let's take a look at everything less than p. So if it's less than p, then of course that means that we're sitting in S, because again, p is an upper bound. So if I'm less than p, then I have to be in S. So now I'm going to write down a couple of inequalities here. So first of all, I know that f of p is less than or equal to L. The reason being, L is an upper bound. Right, so we definitely have to have this. Number two, I can find an x epsilon in F so that this here is true. This is because L is an upper bound. Right, remember our property about upper bound, that I can find an x epsilon in S such that this here is true. Right, so this inequality here means that it's actually sitting in S, because again, it's less than or equal to P. So if it's in S, I'm using the fact that L is an upper bound to say this here. Right. And then finally, this last part over here, this last inequality, this is a little bit silly because the point is that x epsilon is in S, so f of x epsilon is less than L. L is an upper bound. Okay, so to recap, the first inequality here comes from the fact that L is an upper bound for S. The second inequality comes from the fact that L is a least upper bound. And the last inequality comes from the fact that L is an upper bound. Okay, so any questions on how we found these inequalities here? Okay. All right, we have one more inequality. Now, on the other hand, let's say what happens when x is greater than p? Well, now we are not in S. Right, remember, we still have this inequality here, but we are no longer within S. So let's think about this. F of x must be greater than L because remember how we defined S. S is the set of elements where f of x is less than or equal to L. So if x is not in S, then f of x has to be greater than L. Right? So that's where this first inequality here is coming from. So again, x greater than p, so x is not in S, so f of x has to be greater than L. Right? Now, this next statement over here is a little bit tricky to explain, but I'll try my best here. This here also has to do with the fact that x is not in S, but p here is the least upper bound. So you have to kind of stare at this for a little bit, and maybe I'll just kind of ignore this inequality here, just really for the sake of time. But roughly what this says is f of p here has to correspond to the least upper bound for S, but x here is not in S. So you have some kind of inequality over here. It's a little bit difficult for me to try to explain, but that's kind of the rough idea of where the second inequality is coming from. So again, the first inequality here comes from the fact that X is not in S. And the second inequality comes from the fact that P is the least upper bound for S, and X is not in S. All right, so any questions here? Right. Okay, now we're actually done, because now we just say this. We just said that FP is less than L plus epsilon. So that's this part. And we just said that FP is greater than or equal to L plus epsilon. So that there is this part. But now if you put all of this together, that's the same thing as saying this inequality holds for any epsilon. Right, so again, we're just kind of combining the two sets of inequalities that we have so far. So now if we know that this absolute value is less than epsilon for every epsilon, then we have to conclude that f of p equals L. Okay, I'll let you stare at that for a minute and let me know then if you have any questions about what we have here. Okay, all right, so I'll let you kind of stare at that, and then please let me know if you have any questions during office hours. So what about the boundedness theorem? So for the boundedness theorem, we're actually going to do this by contradiction. So for the moment, let's say that our f is not bounded. And of course, we have to show that there's an upper bound and that there's a lower bound. So for the moment, let's just say that there does not exist an upper bound. And it's going to be a very similar proof if we assume that there does not exist a lower bound. All right, so again, we're going to do a proof by contradiction. And let's assume that it does not have an upper bound for the moment. So what that means is that I can find a sequence so I can make this as large as I want. Right, so remember that this is just what it means to say that it does not have a bound. So we could write this here in terms of epsilons and deltas, but if you just remember in terms of what we did for epsilons and deltas, this is exactly that. So for every integer n, I can find an xn where I can now make these as large as I want. So we have a sequence. It's contained in a closed interval, so it's a bounded sequence. The Bolzano-Weierstrass theorem says that it has a convergent subsequence. So let's call that B. But then this convergent subsequence has a limit, call it P. And its limit, of course, has to be between A and B. Right? So I actually didn't say this right. This here was supposed to say that everything is bounded, right? So actually this here is not quite right, the way I've stated this here. So I'm sorry about that. But this here just says that now I have a P inside of this finite region. And so the whole point here is that I do have an element FB, which can't be too large. On the other hand, remember that I have the subsequence. So this here is going to get larger and larger and larger. In fact, this here has to be infinitely large, right? That's the problem. On the one hand, this FP here has to be a finite number. It can't be infinite. It has to be some finite number, some number I compute. On the other hand, f of p here can be as large as I want. So like it has to be infinite. Right? And there's no way that we can have both of those at the same time. Okay. All right, so any questions on how we did here this boundedness theorem? Okay, so let's do the last one. And I'll just kind of skim over this here. So for the last one, we need to prove that we have extreme values. So that is that there exists some C where I hit the maximum on the nose, and there exists some D where I hit the minimum on the nose. And if you want, the way that we can define max and min is, well, let's let S here just be like the image of F. So it's the set of F of X where X is an I, and we'll let lowercase m be the infimum and capital M be the supremum. So first of all, because we're dealing with infimums and supremums, we can find a sequence that gets as close to those two as we want. Right, so again, I can find a sequence, CNs and DNs, where I can get as close to the upper bound as I want, I can get as close to the lower bound as I want. So now, if I stare at these sequences, the CNs and DNs, they're bounded. So by the Bolzano-Weierstrass theorem, they have convergent subsequences. So let's just let C and D be the limits of those subsequences. And then if this is the case, then I just kind of wind through and just realize that C and D are exactly what you want. Okay, so I think for the sake of time, I'll just kind of skim over how this goes here. Okay, so any questions on how we proved these three? All right. So I would say feel free to look over the lecture notes. Certainly I'll be around for office hours in case you do have any questions here. But mainly I wanted to kind of put out there these three propositions to say that these are the three main propositions when it comes to continuous functions. So next time, what I want to do is talk about these three propositions in a bit more detail, kind of go over a few more examples, and then maybe talk about one or two applications thereof. All right. Okay, well, if there's no other questions, then you all have a good rest of the day, and I guess we'll see each other on Wednesday then.
Thank you.
Okay, all right, yeah.
Thank you.
Thanks, everybody.
Thank you.
If you have comments about the grading, please let me know.
Yeah.